this in the past. Alright. Okay, so explain what? 16? Your baseball problem?
My biggest problem was what do you do when you have, like, both problems are a really good example. When you have a velocity, like 1 meter per second, and then you have a distance, you have another distance, and you're trying to find the velocity in x. But what do you do with the fixed distance? If you get, z equals dz over dt.
Well, yeah, it's basically, yeah, so for instance, if you remember problem 18, okay, we were looking at, this is more or less what you're talking about, right? This was 1 meter, or foot, or whatever it was, right? And so the two unknowns are x and y, right? Or z, or whatever you want to call them. So Pythagorean theorem works the same way, just y squared equals x squared plus 1 squared.
Yeah.
So when you take the derivatives, the derivative of 1 is just 0. So you'll just end up with 2y dy dt equals 2x dx dt.
I took the derivative of z and then made the z disappear because dz over dt didn't exist.
Well, yeah, but we don't have any z's because it's a fixed number.
So it isn't really necessary except for finding out what y is.
Yeah.
Would it still work if you just put y as 1 and
You mean like call it a z and then say z equals 1?
Yeah, I just kept z as that part.
Okay.
Did y equals 1.
So z and then y?
Yeah, does that work?
It does as long as you realize that dy over dt is 0, because it doesn't change. So as long as you keep that in mind, because that distance is fixed, then it works.
Yeah.
You kind of make your life a little more complicated, but it doesn't matter. I mean, it does work in the end. Okay, so do I need to talk about 16 then?
Yes.
Okay, which part? From beginning to end?
Yeah.
Okay, so let's see. We have this, last time you made fun of me, so let's see if I can... Okay, doesn't look that bad, right? Say it doesn't look bad. Okay, so this is home plate, first, second, and third base, right? So the problem says that a batter hits the ball and runs towards first base with a speed of 24 feet per second, right? So now, if my batter's right here, and I'm gonna not draw it this time, but if the batter's right there, the problem asks, at what rate is the distance from second base decreasing when he's halfway to first base? So if I denote this by y, then what I'm looking for is dy over dt, right? And now the only thing I have to figure out is I have to describe somehow his speed. Okay? So there's two choices. This is what I was saying last time. There's two choices. I can either define this piece to be x, or I can define this piece to be x. Do you have any preference as to which one to do? This one?
Yeah.
Okay. So if this piece is x, then what is dx over dt? He's running at 24 feet per second. Negative 24 feet per second. Right? Right? Does that make sense? Again, the key idea is it's getting smaller. Right? So the question is, what is dy over dt when x is equal to 45? Right? Does that make sense? Okay. So now all I have to do is just basically connect one with the other. This is a fixed. This is a fixed distance. It's just 90 feet. Right? And so what I have is that y squared is equal to x squared plus 90 squared. Take derivatives of both sides. Simplify and everything else. Dy over dt is just going to be x over y dx over dt. Too fast? 2y dy dt equals 2x dx dt. And if you want to solve for y, you divide by 2y both sides. Yes?
How come for y squared equals x squared plus 90 squared, you can't put 45 in for x squared? Because it's like...
Because x is a variable. So the runner starts at home plate and runs towards first base, right? X is at any given point the distance between the runner and first base, which means it's a distance that keeps getting smaller. We're asked, remember that both of these rates are rates in terms of time, but technically they are functions of time. So the problem asks, what is the rate at a particular time, a particular location in time, which means that's when you actually put in 45 for x. That's basically why I always make sure that when I write it, this is why I write it in this fashion. I say, what is dy over dt when x is equal to 45? And so the idea is, as a general rule, you assume that x is just a variable. Only at the end of the problem is when you put in 45. Otherwise, just think about what it actually means. If I have to actually put 45 in for x, then take the derivative. The left-hand side is just going to be a function. The right-hand side is just going to be 0, because they're just looking at numbers, which means it doesn't change. It's fixed. Does that make sense? Okay. So far, so good? So then now all I have to do is just plug in, what I need to know, right? So I'll cheat. And I'll say that y is equal to, so x is equal to 45, and y is equal to 45 square root of 3. Yes? Any thoughts why that's the case? Yeah? No? Think about your triangle. This side is 45, this side is 90, which means this is a 30-degree angle, this is a 60-degree angle. Think about your trigonometric triangles. 1, 2, square root of 3. Right? Wonderful. Okay. Wrong. The famous triangles. This is 1, this is 2, and this is square root of 3. So, anyway, I'll blame it on I didn't have enough coffee yet. Okay, so now y then is going to equal the square root of 90 squared plus 45 squared, right? So it's equal to 45 square root of 5, and so dy over dt then is going to equal 1 over the square root of 5 times negative, what was it, 24? 24 feet per second. Does this make sense? Yeah? Part B says, at what rate is his distance from third base increasing at the same moment? So what if I would say that for part B, the answer is 1 over the square root of 5 times 24 feet per second. Does this make any sense? It's exactly the same distances. Everything works exactly the same way. The only difference is it's increasing, so it's going to be positive. Yes?
If you did 24 over root 5.
That's fine. I had it written here this way, so I just wanted to maintain it the same way, so you see that it's actually the same thing. The only difference is that there's no minus.
Okay.
Does that make sense? Is everybody understanding why this is the case? I mean, it's exactly the same triangle, it's exactly the same setup. The only difference is the rate is increasing instead of decreasing, so... Okay? Alright, what else? Yes?
Number 66A.
66...
3.2.
3.2. 66A, you said?
Yeah.
Okay. We have 2 less than ln of x less than 9. The key idea is ln of x is a function defined everywhere, right? So it actually can be negative, it can be positive, right? But it's bounded between 2 and 9, which means all 3 quantities are positive, which means I can have 2 to the e to the second. Seriously, I need to drink more coffee. E squared less than e to the ln of x less than e to the 9th. Does this make sense?
Yeah.
Now we have to be careful in general with these types of statements to make sure things are positive and you maintain the same inequalities and all that fun stuff. But because all 3 quantities are positive, I know for a fact it's going to maintain the same the same ratio. Not only that they're positive, but they're also actually bigger than 1. So e to the ln of x is nothing else but x. So that's your answer. Make sense? Yes. 46. Same section. A or B? 46a says 2 to the power log base 2 of 3 plus log base 2 of 5. So now laws of exponents tells us what? That this is the same thing as 2 to log base 2 of 3 times 2 to log base 2 of 5. Yes? Yes? Which is nothing else but 3 times 5, so you end up with 15. Alternately, you can come down here and say this is the same thing as 2 to the log base 2 of 3 times 5, which gives you 3 times 5, which gives you 15. Basically, we have 2 choices of how to handle it. Is this making sense? Yeah? Okay. Part B, you said? Okay, so we have e to 3 times ln of 2. And the key idea is that e to the ln of something is just that something. But in order to get there, you have to actually have it e to the ln of something. So what we can observe is that I can take this 3 and put it inside the ln. So I'll have e to the ln of 2 cubed. So it's 2 cubed, which is equal to 8. So from this point on, whenever something looks interesting, we'll just call it the butterfly effect?
No. It's just that. Moving the exponent around.
Why is that the butterfly effect?
It's part of the butterfly. I don't know why. It's something to remember. You don't have to think about that.
See, I would have assumed the butterfly effect. You would assume is when you talk about inverses and the fact that when you fold them, they actually match exactly. Like for instance, when a function is even, you fold it over the y-axis, and it actually folds. You know the.
No, I like calling that the mirror effect. Butterflies are pretty even.
Okay. Okay. What else?
64B.
64b. Okay, so what we're looking at is the following. We have e to the ax is equal to c times e to the bx. X is 0. X is for sure not 0. That's guaranteed that 0 is the only one that doesn't work. Why? E to the 0 is 1, right? So e to the 0 is 1. 1 equals c. So as long as c is not equal to 1, then that actually can't happen, right? So how do we solve it? We apply ln both sides. So we have ln of e to the ax is equal to ln of the quantity ce to the bx. Now what do I get on the left hand side? Ax. What do I get on the right hand side? Very good. ln of c plus bx. Yes.
Couldn't you just do the butterfly effect? Remove the c, the bx.
How can you do that? That only works for natural logarithms. This is an exponential.
Oh,
Right?
yeah.
Is this making sense? I on purpose did not write it first. I wanted you to tell me the answer because I wanted you to tell me why that's the case. Yes?
Doesn't on the right hand side, doesn't the ln and the e like cancel each other out?
They would, but you have the c to deal with. So on the similar to the similar problem, yes. The previous problem. Today is going to be a fun day. You can't do e to the ln here until you actually manage to get rid of the 3. Right? So we put in the 3 in first, and then we add e to the ln, so we only get the stuff. Similarly, when you come down, you can't deal with the c first. So what you have to do is you have to use laws of logarithms to say this is ln of c plus ln of e to bx. Because it's a product. And now the second part becomes just bx. And so now all you have to do is solve for x. So I'll skip the complicated algebra. This is ln of c divided by a minus b.
Yeah, I don't see what's complicated algebra.
I was being sarcastic.
It wasn't complicated?
I should raise my hand from now on when I'm being sarcastic. The bx moves to the left, factor out an x, and then you divide by a minus b. Yes? 74? The limit is 1. Sorry, the limit is 0. I don't know if that helps. That helps? No. Okay. I did 73 on purpose to give you a hint of how to tackle 74. You have the limit as x goes to infinity of the natural logarithm of 2 plus x minus the natural logarithm of 1 plus x. And so the first thing to observe is that this is the limit as x goes to infinity of the natural logarithm of 2 plus x over 1 plus x. And now if we take things separately, we haven't really talked about this, and it's kind of funny that the author of the book kind of assumes that we can do this without actually saying things, but in reality Because ln is a continuous, strictly increasing continuous function, then this is actually the same thing as the ln of the limit as x goes to infinity of 2 plus x over 1 plus x. And that limit is just 1, so you end up with ln of 1, which is equal to 0. Last time what I did is I actually took separately the limit of the fraction, and then I said since that was infinity, then the answer is just ln of infinity, right? But for both situations, the idea is, the assumption is that you can actually replace ln with limit, or you can interchange their order. And you can do that because ln is actually a nicely behaved function. And this is actually something that we're going to be using a lot when we get to section 3.7, which is L'Hopital's rule, which is just nothing else but limits. So if you think you got away with, away from limits, sorry. However, I think you'll probably enjoy section 7.
As in not enjoy?
I didn't raise my hand. I think you will enjoy it because you're actually going to find ways to actually come up with limits in a much easier format, I think. Okay. What else? 26 from where?
3.2.
Okay, so y is equal to 1 plus e to the x divided by 1 minus e to the x. And we're supposed to solve to find the inverse. So this was step 1. Step 2 says x equals 1 plus e to the y divided by 1 minus e to the y. And step 3 was solve for y. So first things first, we have x times 1 minus e to the y is equal to 1 plus e to the y. Yes? So far so good? And now x minus x e to the y equals 1 plus e to the y. We'll come on this side over here. And then we have e to the y multiplied by 1 plus x is equal to 1 minus x. X minus 1. So far so good? Yes? I moved the this quantity this way, this quantity that way, and factor out an e to the y. Okay, so now e to the y is equal to x minus 1 over, I'll write it as x plus 1 so it looks nice and pretty. And so from here y is just ln of x minus 1 over x plus 1. Okay? Alrighty. Ready, set, go? Okay. That sounds exciting. That sounds exciting. What class is that? 131 or 141?
Rhetoric, writing.
Thank you. Alrighty. So, I'm sure everybody's very excited to find out what the derivative of ln of x is today? Well, at least you can fake the enthusiasm. All right. That's the spirit. All right. So first things first. We're going to look at f of x equals log base a of x. So we're going to try and figure out what the derivative of log base a of x is. Okay? Now, bless you. How should we approach that? Yes?
Convert it into an exponent.
Why? We don't know what the derivative of an exponent is.
Yeah, don't we just move it down? And then do the whole...
Under no circumstances is the derivative of 2 to the x times 2 to the x minus 1. Sorry? Here? Well, or here. We're trying to find the derivative, right?
Oh, okay.
So that's basically our ultimate goal. We're trying to find derivatives of logarithmic functions and exponential functions. So we're going to start with the derivative of a logarithmic function, and then we're going to look at an exponential. So when in doubt, use a calculator. Well, you're in luck because I don't allow calculators for tests. So.
You know, that actually makes it a lot easier, because then these are problems are super complicated.
That's, I don't, as I said in the beginning of the semester, I don't want to test you on your punching skills, as in punching into the calculator. So I'm much more interested in if you actually know how to solve a derivative or an integral rather than actually multiplying things. Okay, so the limit as h goes to 0 of f of x plus h minus f of x divided by h. What do we call this formula, by the way? For those of you who... the definition of a derivative, right? Okay. Without the limit is called a difference quotient, right? But because we're taking the limit, we're actually talking about the definition of the derivative. So, we have log base a of x plus h minus log base a of x divided by h. Right? And so this is equal to the limit as h goes to 0 of, I'm going to write it in this fashion, 1 over h times log base a of x plus h over x. Everybody follows that?
Okay.
Yeah? So I did two things. First of all, I wrote it as 1 over h times whatever the numerator was. And then using laws of logarithms, I combined the two logs into the log of the fraction. Okay? Now the other thing we can do is we can write this as 1 over h times, sorry, I can't do that. The limit as h goes to 0 of 1 over h times log base a of 1 plus h over x. Right?
Oh, yeah.
Okay. Okay, now the next step is going to be not going to become apparent until I'm actually done with this. I'm going to have 1 over x times x over h log base a of 1 plus h over x. So I multiplied and divided by an x. Okay? So far so good?
No. What just happened?
I multiplied and divided by an x.
Yeah, why?
Patience. Now, 1 over x does not depend on h, which means I can take it outside of the limit. Right? Moreover, using the butterfly effect. This is equal to 1 over x times the limit as h goes to 0 of log base a of 1 plus h over x raised to the power x over h. Right? There is no shortcut.
Oh no.
There is no shortcut, but once we actually get the derivative, we're not going to have to do this again. We can just apply the chain rule and come up with the derivatives. Okay, so far so good?
Oh wait, okay. See where you has the red box?
Uh-huh.
Seems like we split the 1 over x and the x over h. Like we send them to each side.
What I'm saying is that the limit is as h goes to 0 doesn't depend on x, or x doesn't depend on h. Right? Which means I can take it outside of my limit. Okay? So that's what happened with the red box, and then I used the laws of logarithms to move x over h to the exponent.
Now, is that law they say
Of the whole thing.
by?
This is the argument of log.
Okay, and that is multiplied by that limit.
This is the limit of this. So the only multiplication happens right here. It's 1 over x times the limit. Okay, now exactly the same as before. This is 1 over x times log base a of the limit as h goes to 0 of 1 plus h over x divided to the power x over h.
We move the log of a outside the limit as well.
The log and the limit. Remember what I just talked about in the homework problems I was doing. I said log is continuous, it's strictly increasing, so you can actually interchange the log and the limit.
So if there's a log there, we can probably put it outside the limit.
Yes. Okay. Now, what is this limit? E. Very good.
That's a good guess.
Because that was the definition.
The definition of E was the limit as x goes to 0 of 1 plus x to the 1 over x. Right? Remember this?
No.
Wonderful. Let's make them wise to make it simple, clearer. Y goes to 0 of 1 plus y to the 1 over y. Now if I define y to be h over x, clearly as h goes to 0, h over x goes to 0. Right? X is just a fixed number. Right? So that means that y goes to 0. Then I have 1 plus h over x, I define that to be y, to the power of 1 over y, but that's just x over h. Does that make sense? If you think about it, here, let me clean this up, I guess, so it actually looks a little better. So y goes to 0 of 1 plus y divided by 1 over y. So if you define y to be h over x, then 1 over y is just x over h. Does that make sense? Which says that the derivative of log base a of x is equal to, now before I actually write the actual formula, let me write it in a nicer way, because 1 over x times log base a of e doesn't look very nice. With the change of base formula, I can write this as 1 over x times ln of e divided by ln of a. And you might ask yourselves, why is that actually simpler? Well, what's ln of e? 1. And so my derivative is just 1 over x times ln of a.
Oh wait. So with ln of e over ln of a, that destroys the log.
That's the change of base formula. We change the base from a to e. So far so good?
A can't be 0 or negative?
Sorry?
A cannot be 0 or negative.
No, well, it never will be. Remember, log base a of x is equal to y is equivalent to a to the y is equal to x. And we defined a to the x or a to the y for all positive a's. So it will never be 0. And moreover, x can't be 0 because the domain of log base a of x is everything positive. So this makes sense at all times. Does this make sense? Okay, wonderful. So now, what would you guess the derivative of ln of x to be? One over x. Does that make sense? ln is log base a, is log base e, right? Yes? So log base e of x, which is ln of x, is equal to 1 over x times ln of e, which is just 1. So you end up with just 1 over x. Okay? Alright, so now, let's see. What should I do? What would you guess the derivative here? Let me write it here as well. What would you guess the derivative of ln of g of x to be? Times g prime of x. Chain rule. Does this... I'm trying to come up with a different word and make sense considering I said that about 15 times already. Can you follow this? Again, this is just a chain rule. The derivative of ln of x is 1 over x. So if I have anything except x here, I have a function as in ln of g of x, then when I take the derivative, it's just going to be 1 over g of x times the derivative of g of x. Okay? Yes? Okay. Alright. For motives that are going to become apparent basically close to the end of the semester, what would you guess the derivative of ln of the absolute value of x to be? So let's look at the definition of ln of absolute value of x. It is ln of x when x is bigger than 0, and it's ln of minus x when x is less than 0. Right? Notice one thing that's missing there. X equals 0, since ln of 0 doesn't make any sense. Right? Okay? So then, what is the derivative of ln of absolute value of x? Well, it's going to be 1 over x when x is bigger than 0, and it is 1 over minus x times negative 1 when x is less than 0.
Where is that negative 1?
The derivative of minus x.
Oh, yes.
Which means that the derivative of ln of absolute value of x is equal to 1 over x. Okay? Alright. Let's see, how are we doing on time? Okay, well, I guess we're still relatively good. Let me define the derivative of the exponential functions first, and then maybe we'll go and look at some problems, because they actually have them mixed up, so it's easier this way. So, first step, f of x equals a to the x. What would you guess the derivative to be?
No, x.
let's see. Can I do this first? Maybe I shouldn't do this first. Let's step aside for a second and actually do. So before I do this, so you actually see why it works. Let's look at, for instance, problem 47 on page 167. Y is equal to sine squared of x tangent to the fourth of x divided by x squared plus 1 squared. What we're looking for is dy over dx. And you can see how ugly it could potentially look when you take the derivative. But what we're actually going to do is we're going to use logarithmic differentiation. What is that actually doing? If we apply natural logarithms both sides, we end up with ln of y is equal to ln of fraction sine squared of x tangent to the fourth of x divided by x squared plus 1 squared, which means ln of y is going to equal 2 times ln of sine of x plus 4 times ln of tangent of x minus 2 times ln of x squared plus 1. Does this make sense? Yes? Now, one of your favorite topics. That's another one. No, this one is implicit differentiation. What happens if I take derivatives with respect to x on both sides? What do I get on the left-hand side? 1 over y times dy dx equals, what's the derivative of ln of sine of x? Two times cosine of x over sine of x. Right, because it's 1 over sine times the derivative of sine, which is cosine. Yes? Okay, plus 4 times secant squared over tangent minus 2 times x over x squared plus 1. Right? Which means that dy over dx is equal to sine squared of x tangent to the fourth of x divided by x squared plus 1 squared multiplied by 2 times cosine of x over sine of x plus 4 times secant squared of x over tangent of x minus 4x divided by x squared plus 1. Does this make sense? What I've done is I solved for dy over dx, which means I multiply both sides by y. The fraction is just y. It's the original y.
Is there a formula for that? What's it like that?
For what? For this particular thing? This is called logarithmic differentiation.
I meant for like where did we get the original equation back from?
It started off, that's what we started off with. Right? We started off with y equals sine squared tangent to the fourth. And then on the bottom of this page, right before I started the new page, I have 1 over y times dy over dx equals all this mess. So to solve for dy over dx, you just multiply by y, which is y. I just didn't want to write 2 lines. So this quantity is just y. Well, it was 1 over y originally, so when you multiply both sides, you just end up with y. This is logarithmic differentiation.
Why is that quantity blue line again?
You're trying to solve for dy over dx, which means you multiply by y both sides.
Okay.
So the left-hand side is dy over dx. The right-hand side is that whole bracket, which is the top part, times y. Y was given to be sine squared times tangent to the fourth over that mess. Is everybody seeing this, or do you want to see another problem like this?
That's our final answer.
That is the final answer.
So we don't have to seriously derive why. Probably not.
No. Should I do another one? Okay, 51. You should enjoy this one.
I see the hand.
Cosine of x
Yeah, where's the
to the power x. Now we haven't actually learned how to take derivatives of exponential functions, and we'll do that as soon as I'm done with this problem. But before we get there, notice what we're actually looking at here. We're looking at a function raised to another function, which means you can't apply the product rule, nor can you apply the derivative of an exponential function, which, as I said, I haven't actually defined yet, and we'll see in a second how to do. So how do you actually come up with the derivative of this function? There's only one way, and only one way of doing that. ln of y is equal to ln of cosine of x to the x power, which means ln of y is equal to x times the natural logarithm of cosine of x. And now we implicitly differentiate both sides. What do you get on the left hand side? 1 over y dy dx. What do you get on the right hand side? Product rule. X times ln of cosine of x. So the derivative of x times ln plus the derivative of dln times x. So that'll be negative sine of x over cosine of x multiplied by x. And so dy over dx.
Did you do some chain rule there?
Yes. dy over dx is equal to cosine of x to the x power multiplied by the natural logarithm of cosine of x minus x times sine of x over cosine of x. Obviously, you can write these as tangent, and the other one was cotangent if you want. That's not necessarily all that important at this point. Does this make sense? Again, this is actually the only way you can take the derivative of that function. There's no other way. Okay, so let's look at exponential functions. So f of x is equal to a to the x. Let's try and find out the derivative of a to the x. We don't know how to take it, the derivative, but we can be sneaky about it. Y equals a to the x, which means ln of y is equal to ln of a to the x. And so ln of y is equal to x times ln of a. And if I take the derivatives on both sides with respect to x, what do I get on the left hand side? Okay, and what do I get on the right hand side?
X 1 over a
You said ln of a?
Yeah.
And that's it? A is a number. ln of a is a number. This is just x times some number. You take the derivative, you're just going to end up with the number. Yes? So dy over dx is equal to y times ln of a, but y is a to the x, and so the derivative of a to the x is equal to a to the x times ln of a. Right?
So we still need the y times the derivative.
Yes. Is this making sense?
Partially.
Okay, as promised last time, I'll actually show you the most interesting derivative in all calculus. What is the derivative of e to the x? E to the x. As promised. It doesn't matter what you do to it, it stays the same. Do you see this?
Natural log of e is 1.
Because natural logarithm of v is 1. So then what is the derivative of e to g of x? E to g of x times g prime of x. The fundamental thing that you need to take out of this particular section right here is whenever you take a derivative of an exponential function, the exponential function stays. It doesn't go away. Notice I took the derivative of a to the x. I still have a to the x. Multiply by some other thing, but I still have a to the x. I take the derivative, bless you, I take the derivative of e to the g of x. Again, I still have e to the g of x multiplied by something else. Okay? Alright, so let's look at some problems. Let's see. Start off slowly or faster? Speed of light?
No, I'm just kidding.
F of x equals log base 2 of 1 minus 3x. So the question is, what is f prime of x? Do you remember what the derivative of log base a of x is? It's 1 over x times the ln of a. Right? So what happens if I have a function? The chain rule tells me that this is going to be 1 over 1 minus 3x times ln of 2 times negative 3. Does this make sense? Again, the idea is the derivative of log base a of x is 1 over x times ln of a. So I have 1 over whatever this was times ln of a. And then I have to have times the derivative of the stuff. So I end up times negative 3. Okay, number 5. F of x equals the 5th root of ln of x. To the 1/5. So this is the same thing as ln of x all raised to the 1/5. Please be advised that it's not ln of x to the 1/5. It's ln of x as a function raised to the 1/5. So what is the derivative? One-fifth 4/5 times 1 over x. Okay? And so we have 1 over 5x times ln of x to 4/5. Okay, how about number 7? F of x equals sine of x times the natural logarithm of 5x. So what are we looking at? We need a chain rule for what? We need a chain rule for this 5x, and we need the product rule for these two functions. So, what is the answer? And that was a question. Cosine x, ln of 5 of x,
Where did that find?
what's the derivative of 5x?
That's the
Chain rule. It's 1 over 5x times 5, or it's 5 over 5x. Right? Which, by the way, shouldn't really surprise you, because ln of 5x is just ln of 5 plus ln of x. So if you take the derivative, ln of 5 is just 0. Okay. How about 11? Since everybody looks at me like, what in the world are you actually talking about? Ln of fraction 2t plus 1 cubed divided by 3t minus 1 to the 4th. So the one thing I could potentially do is actually apply the formula for the derivative of ln. So it'll be 1 over this lovely creature times the derivative of this. But do we really want to take the derivative of this? So what can we do? Laws of logarithms tells us that that's just 3 times ln of 2t plus 1 minus 4 times ln of 3t minus 1. So now when I come and say what's f prime of t, my problem should be much simpler, right? Shorter way or longer way? Long. 3 times 1 over 2t plus 1 times 2 minus 4 times 1 over 3t minus 1 times 3. Okay, so obviously you can write it as 6 over 2t plus 1 minus 12 over 3t minus 1. 17. F of x equals x squared e to the x. So what would f prime of x be? Two x e to the x plus x squared e to the x.
Oh yeah, because the derivative of e to the x.
It is just e to the x. Okay? Alright. Let's see. How about 21? Y equals x e to the minus x squared. So what is the derivative? E to the negative x squared plus x times e to the negative x squared times minus 2x. No, I don't. I just wanted to simplify it to signify that the brackets are the derivative of e to the minus x squared. Is everybody seeing that? Again, remember what I said. When you take the derivative of an exponential function, regardless of what else shows up, the exponential function is still going to remain there. It doesn't go away. Okay? Obviously, you can work out the algebra and have it minus 2x squared and so forth. How about 23? Y equals e to the power x times cosine of x. I'm waiting. E to the x cosine of x times
We have no x, constant quantity.
chain rule. Cosine of x minus x sine of x. Yes? That's good. I empowered you with knowledge. T cubed minus 3 to the t. So what is h prime of t? You all know what the derivative of t cubed is, right? 3t squared minus, now what is the derivative of 3 to the t? 3 to the t, ln of 3. Yes?
Why is that?
Because the derivative of a to the x is a to the x times ln of a. Okay? Let's see. 29 would be interesting. What are we doing on time? Okay. Y equals 2 to the sine of pi x. So what should we observe here? First thing is the fact that it's an exponential function, right? It has a base different than e, so there will be an ln of 2 at some point, right? The other thing to observe is that I have 2 to a function of x. So when I take the derivative, the chain rule has to come into play, which means my derivative is going to be 2 to the sine of pi x multiplied by cosine of pi x times pi multiplied by ln of 2. Yes? No.
Where's the ln of 2 come from again?
The derivative of a to the x is a to the x times ln of a.
Okay.
Everybody sees where everything's coming from? Do you see the pi? It's a double chain rule, right? You're looking at sine of pi of x, or pi times x. So you're looking at two functions, right? Function of a function. How about 39? Y is equal to x ln of x. We're asked to find the first and the second derivative. So, to get to the second derivative, we need to come up with the first derivative, right? What is the derivative of x times ln of x? Ln of x plus x over x, which is 1. Everybody sees that?
X times 1x.
Yeah. Okay. So then what is d squared y over dx squared? Remember, that's the notation of the second derivative. Just 1 over x. Is that making sense? Well, of course, yours for the homework is much more complicated. It's ln of quantity secant of x plus tangent of x. Okay. How about 41? It's not my fault. Stuart makes even problems harder than odd ones. I know. I just don't want to say it out loud. ln of x and the point 0 in e. You didn't think we're going to go through a whole class section without actually talking about tangent lines, right? So the equation of a tangent line going through the point E and 0. Why not? So what do you have to do first?
Find the derivative.
Find the derivative. What is the derivative of ln of x? 1 over what? Times 1 over x. Chain rule. The derivative of the first ln, maybe I should have color coded it. The derivative of the first ln is just 1 over the parentheses times the derivative of the parentheses, which is just 1 over x. Okay? So now all we have to do is dy over dx at the point E and 0 is equal to 1 over ln of e times 1 over e, which equals 1 over e. So the equation will be y minus 0 equals 1 over e times x minus e. Right? Okay, 55 or 57? And I won't do the average between 55 and 57. I mean, not today. I'll probably end up doing it on Monday or something. But 55 or 57?
Everyone's harder.
I don't know.
Only 57.
Y equals the natural logarithm of the quantity x squared plus y squared. We're asked to find dy over dx. So we take derivatives both sides. By the way, when you look at this, do you notice that it's implicit differentiation? Sorry? Because the right hand side has y in it.
Oh, okay.
It's ln of a function of y, and you can't actually solve it for y. So the left hand side is just going to be dy over dx. What is the right hand side? One over x squared plus y squared times 2x plus 2i dy dx. Right? And I'm sure Everybody can solve for dy over dx?
No.
Too bad.
Actually, I probably could.
Right? Multiply x by x squared plus y squared, both sides. Combine terms alike. Move all the terms not involving dy over dx. Divide by whatever you factor out. Okay, we'll stop here. Since you all sounded so confident that you can do it.